Buonasera, buonasera.
Good afternoon from the Museum in Trento. And we have few people in the audience, welcome, but there are many people following via the website of the Festival of Economics. So welcome, and welcome Professor Naomi ORESKES. I should say good morning to Professor ORESKES rather than good evening or good afternoon, because she is with us from Boston. She is a professor of the history of science at Harvard University. Thank you very much for participating in this event. I will soon give you the floor. And before doing so, I will say that over the past months, with COVID, we often heard people saying that we rediscovered the centrality of science and scientific knowledge, also in Italy, where for many years it was so that scientific knowledge played a marginal role, actually, in the cultural and political and social life of the country, leaving a space also to the spreading of pseudoscience also within the sector of science. So if it is so that the COVID pandemic reopened our eyes about the value of science at the very moment when we discussed about the crisis of trust, or rather distrust, towards science. So in this moment, it's important that we reason about our relationship with science and the role of scientists in society. These are the topics which are the focus of the studies of Professor ORESKES. And this is also the subject matter of her latest book, Why Trust Science, which we hope will soon be translated into Italian, because this helps us understand how scientific knowledge is built without neglecting the limits, constraints, and failures also of something which is absolutely human. This is useful in our battle against COVID, because we often ask and demand from science that we get immediately a response and an answer, and we so misunderstand the role of science. Naomi ORESKES is a geologist. And at Harvard, she also works, she's an affiliated professor of Earth and Planetary Sciences. And you reasoned a lot on the relationship between science and society and climate change. This edition of the festival is devoted to growth and environment. The pre-assumption, so to say, is the knowledge that we already suffer the influences of climate change. And so we have to think about the future based on that. And yet, deniers of climate change, with all the forms that they take, from those denying that there is a role played by humans in climate change, and the others who say that there is change, but we shouldn't be worried. So this group of deniers is very present in Italy, and certainly must be present also in the United States, so much so that there is a member of this group at the White House. So Naomi ORESKES has many merits. One of them is the fact that she wrote the book Merchants of Doubt, that was published 10 years ago and translated into Italian last year, actually. In that wonderful book, she explains how distrust and trust work in relation to science, and the fact that there are groups linked to various lobbies and the various sectors that raise doubts about, for instance, the human influence on climate change. So she explains methods in understanding what bad science is, which is rooted in the tobacco strategy, which was created to contrast the emerging of scientific evidence linking tobacco and many diseases. But that happened also with evolutionary theory and vaccines and the ozone layer. So after 10 years, it is so that this system of discrediting science has found new ways of being widespread through social networks. So now I would like to give the floor to Naomi ORESKES to try together to understand better whether we can save science, which is the title of our meeting today. So what can we do, citizens, and how are things? So you have the floor, Professor ORESKES.
Well, thank you very much. Grazie and buona. It's really a pleasure to be with you all today. I'm sorry that I can't be with you in person to eat good Italian food and drink good Italian wine, but this will have to do as the next best option. As you heard, I'm the author of the book Merchants of Doubt, which was just this year translated into Italian. So I hope that you'll all have the opportunity to read the book. But today I want to talk to you about my new work, this book, which I happen to have right with me, Why Trust Science. And as you just heard, we hope we can get this translated into Italian. So if there are any publishers out there, please email me after the meeting. This work is especially timely in a sad way. We have seen this year through COVID-19 that the cost of distrusting science is very, very high, that science truly is a matter of life and death, and therefore understand not just the science facts, also the processes by which scientists come to their conclusions is urgent for all of us. And it's urgent for us to be able to understand not that we have a blanket faith in science, because that would not be warranted, but that we understand science well enough to make intelligent decisions as citizens, as families, and as countries. And so that's what I'm going to talk to you about. So even before we were already facing a number of important and contested issues regarding scientific information. Should we vaccinate our children? Should we accept genetically modified crops? What should we do about climate change? And now, of course, should we wear masks? And will a vaccine for COVID-19 be safe? One of the challenges we face as citizens is that the science around these issues often seems very complex and rather uncertain. Scientists work at the boundary between the known and the unknown. So by definition, there will always be uncertainty at that boundary. And sometimes that certainty can set grounds for doubting the science or even rejecting it. And sometimes that uncertainty is deliberately exploited by actors like the tobacco industry or the fossil fuel industry. So what do we do as citizens? Well, starting in the early 2000s, I began working on the issue of climate change. My own work in the history of climate science showed that by the early 90s, there was an extensive scientific literature affirming the reality of the human causes, or what scientists like to call the human fingerprint, climate system. But this led many people to ask me, well, why should we trust the scientists? And I realized that that was actually a fair question, even if it was sometimes asked in a kind of skeptical and belligerent way. To accept the safety of vaccinations or the reality of climate change, we have to trust science. We have to accept and believe and use the claims of scientists. And that raises a troubling dilemma because for many people, when we talk about belief, if we talk about believing in science, it sounds like faith. And faith seems to be the domain of religion. Most of us have been raised to think that science and religion are two different things. So how can we talk about belief in science? Well, for me, a good place to start to answer that question has to do with the great 17th century philosopher and mathematician Blaise Pascal. Pascal is famous for many things, among them what is known today as Pascal's wager. Pascal said that the greatest question of all was not a scientific or mathematical question. The greatest question of all was, does God exist? And he concluded, let me go back for a moment. He concluded that the best way to answer that question was to say, well, what happens if I believe in God and he doesn't exist versus what happens if I don't believe in God and he does? And Pascal says, well, the latter is worse because I will believe it. I will end up burning in hell. And therefore, it's much less risky to believe in God than not to. And so he clutched for what one of my professors in college said, the handrail of faith. Hold on to that faith because it was less risky than the alternatives. But this raises the question, is science a leap of faith? Most of us have no idea how to judge whether or not scientific claims are true. So we take the leap of faith. We hope for the best. And like Pascal, we assume that the risks of accepting science are smaller than the risks of rejecting it. At least that's what most of us do, but definitely not all. And again, we've seen in recent months how many people have rejected scientific evidence about COVID-19. In fact, the risks have been very, very great. The standard, most common answer to the question that I've just posed is that we should believe in science, we should trust the results of scientific work, because scientists use the scientific method. And by this, the implication is that there's a method by virtue of which the results of scientific work are true. Typically, this method is considered to be what philosophers call the hypothetico-deductive method. By that, they mean that scientists develop a hypothesis, deduce consequences, and then go out into the natural world or do an experiment to observe whether or not those consequences are true. If they are true, we accept the hypothesis. If they're not, then we reject it. Now, there are some very great examples in the history of science where we can find scientists following the hypothetico-deductive method. The most famous of all probably is the bending of starlight, predicted by the general theory of relativity. Einstein said that if space and time are not empty and absolute, as Newton said, but rather are part of a manifold that is bent in the presence of bodies, so that space actually had a fabric, and that fabric had texture, then we could detect that during an eclipse when light from a distant star would be bent as it approached the sun on its way to the Earth. This experimental test was performed in 1918 by the British astronomer Sir Arthur Eddington, and lo and behold, it turned out to be, and this was taken as a great proof of the truth of the theory of general relativity. Now, there's a problem, though, and the problem is that logically, this method doesn't actually work. It doesn't hold up logically. And there are a couple of reasons why that's true. The most famous is called the fallacy of affirming the consequent. Put in plain language, that means that a false theory can make a true prediction. So just because our predictions come true doesn't actually prove that the theory that it came from is true. The most famous example of this in the history of science is the Ptolemaic system of the universe, which was so famously overthrown by Copernican and Galileo. Ptolemy held that the Earth was the center of the universe, that planets were on celestial spheres that rotated around the Earth. We would today, this was wrong, that it was incorrect, and yet this model of the universe made very, very accurate predictions of the motions of the planets and of the eclipses. The second problem is the problem that philosophers refer to as auxiliary hypotheses. By that we mean that when we make a test of a theory, like the Copernican system in the universe, we're not actually just testing that theory or that hypothesis. There are also other assumptions that we are making that are built into the test, whether we realize it or not. A very famous example of that comes from the challenge or the debate over the Copernican theory of the universe. So when Copernicus and also Galileo said that the Earth was moving, many critics said, well, if that's true, using a hypothetical deductive framework, then we can deduce that we ought to be able to detect those effects. And one of the effects that people suggested we could detect was something called the stellar parallax. So this illustration is sort of oversimplified version of the stellar parallax argument. The idea here is that if the Earth is moving, so here it is in December, 6 months later it's here in June, if we look at a particular distinctive star in the horizon, then in December we will see that star against a particular backdrop of other distant stars. But come June, when we look at that same star from a different angle, we will see it against a different set. And that angular difference between what we see, what we see in June versus what we see in December is called the stellar parallax. So astronomers did this test. They looked for the stellar parallax and they found nothing. So according to the hypothetical deductive model, we, or they, should have rejected the Copernican theory. It failed the hypothetical deductive test. Now, of course, today we would say that the Copernican theory is right and that the Ptolemaic theory was wrong. So what went wrong in this test? Well, in hindsight, we can see that there was an auxiliary assumption in this test. The assumption was that the universe was small and that the stars were relatively nearby, or put another way, that the Earth's orbit was large compared to the distance. The stellar parallax would be big and it would be easy to detect. Today, we would say that that's not true, that the universe is infinitely large, that the stars are very, very far away, and the stellar parallax does exist, but it's very, very tiny, very hard to detect. In fact, it wasn't until the 19th century in the work of Sir William Herschel, so more than 200 years after Copernicus first proposed his theory, that telescopes became sensitive enough to detect the stellar parallax. So we could say that there was a second hypothesis at work, the assumption, the faulty assumption that the telescopes were sensitive enough to detect the effects. In hindsight, I would say that that was wrong, even though the theory itself was right. But there's also another problem. If the deductive model did work, a lot of science just doesn't fit it. Scientists do a lot of other things other than testing their deductive consequences of theory. The most famous example of that, of course, is Sir Charles Darwin. Darwin's theory of species by natural selection was not deductive. It was what historians and philosophers call inductive. Inductive science is when you don't necessarily have a hypothesis or a theory to test, but you go out into the world and you observe, you look, you see there, and then after some period of looking, you come to a general conclusion about what it is you think you're seeing. And that's what Darwin did when he developed the theory of evolution by natural selection. Scientists also do many other things. We only have half an hour today, so I'm going to speak very briefly about some of the other activities that scientists do. But an important additional method of science is modeling. When you build a model, it could be a physical model like this one shown here in this picture, or some other, it could be an electrical model or a chemical model, or in today's world, a numerical simulation model, a computer model. In the 19th century, scientists built physical models. This is a picture of Henry Cadell, who was a 19th century geologist who was trying to understand how mountains were built. He was interested in the Swiss and Italian Alps. And he was interested in a phenomenon seen in the Alps known as nappes, big folds where the rocks appeared to have been folded back upon themselves, often with large faults cutting across them, in which the rocks, even though we think of rocks as being hard, we talk about things being solid as a rock, but these rocks seem to have behaved as if they were soft, as if they were clay. And so he made a model using clay and sand to try to simulate the effects that he and others had seen in the Alps. And what he argued was that these effects could be explained if the rocks had been pushed from the side by some force. And so here in this contraption, he's developed a device to push the model from the side. And lo and behold, in fact, he does produce features that look very similar to what he sees in the Alps. And this became an early argument in favor of the theory of continental drift, that mountains were caused when continents moved horizontally across the Earth. Now, nowadays, models are typically not made of clay and plaster and sand. Typically, they're made with computers. This is an example of an early simulation model produced by the IPCC, testing the question of what was driving the change in temperature that we have seen on the planet since the Industrial Revolution. So in this model, this black line here represents observations. These are the actual temperatures of the Earth, the actual average temperature of the globe since the year 1900. And you can see very clearly from the observed data, so this is reality, that starting around 19 or a little before, there's a big increase in average global temperature. And this is the increase that today we would say we know is driven by human activities, mostly greenhouse gases. In this model, the question is, this is posed as a question to say, well, what could drive the observed change? This model includes a whole bunch of different things that we know can climate. These are sulfate particles from air pollution. This is dust from volcanoes. This is variations in ground level ozone. This is variations in sunshine and solar radiation. And this is the decrease in greenhouse gases. And look at this picture. The only way you can reproduce the observed result is through all of the above, putting all of these factors together, but it's the greenhouse gas increase that is most clearly linked to the driving the increased temperatures. So here the computer model is used to try to produce what has actually happened in the real world. Because of this diversity of methods, the philosopher Paul Feyerabend once famously said that the method of science is, quote, anything goes. Now, he's often quoted as saying that, as if he was some kind of epistemological anarchist. But actually what he really said, the full quotation is a little bit more subtle. He said, if you would ask me, if you would insist that I tell you what the method of science is, I would have to say that the only principle that does not inhibit progress is anything goes. In other words, scientists are creative, they're innovative, they figure out different ways to answer their questions. So most historians have therefore concluded that actually there is no one scientific method. There are set methods that scientists have used at different times and places. So that leads to the question, what, if any, do these different diverse methods have in common? And I think the answer to that question is evidence. That all these different methods, whether they're inductive, deductive, modeling, etc., are all means of generating evidence about objects and processes in the natural world. They're based on experience, on observation, and on experimentation. The different means of gathering evidence are ways that scientists use to come to agreement about the natural world. And when scientists come to agreement, that's when we say that something is known. This is why I and many other historians, sociologists, and anthropologists of science have in recent decades become very into the problem of scientific consensus. Because what we call scientific facts are really no more or no less than matters about which experts have come to consensus after considerable discussion and argument. Now, so this is the central argument of my book, and if you want to know more about it, again, I invite you to buy and read the book in English if you can, or hopefully in Italian next year. But what I have found since the book has come out is many people like it, many people agree with most of it. The part that they don't always like, the part that upsets many people, is that this seems to be an appeal to authority. It seems to be that I'm just saying we just have to accept whatever scientists say. And many of us have been taught that the appeal to authority is a logical fallacy, that we shouldn't believe something just because an authority figure says so. Well, so I'm going to argue that actually science is an appeal to authority, but it's not the authority of any one individual. It's the authority, the track record of the process, of the scientific process of observing, of demonstrating, and of coming to conclusions based on evidence. So in this picture, you see this woman who's clearly a scientist because she's wearing a white coat, and she's showing her colleagues something. And what is she showing them? Some photographs, some graphs. She's showing them evidence. Now, I always like to say I'm a little suspicious that these people are actually scientists because they look far too happy, but we'll set that aside and we'll just assume that these are, in fact, happy scientists. But the important point here, the really crucial point of my argument, is it's not the authority of the individual scientist, no matter how great or that scientist is. And we really do ourselves a disservice when we focus too much on great individuals like Einstein or Galileo or Pascal. That we need to focus much more, in order to understand science, we focus much more on the process. We can think of science as being a jury of scientific peers, but however we want to think about it, what we come to is the conclusion that what we call scientific knowledge is the intellectual and social consensus of affiliated experts based on the weight of available empirical evidence and evaluated according to diverse but time-tested methodologies. So it's not anything goes. It's a lot of So, but they all get evaluated by the scientific community, who argue, who debate, and to agreement or not. I want to close with just one analogy, but I need to just take a second here because my power is about to run out, and I don't know why. So, okay, it looks like my cord became a little loose, so hopefully we're okay. It would be bad to lose power right at the end here. So if we think about modern technology, think just for a moment about the modern car. The modern car is an extremely efficient and effective and reliable instrument. And how is that? It's not because of the brilliance of any one individual. It's not because of the brilliance of Daimler, Ford, or Benz. It's because the modern car is the accumulated result of 100 years of experience, expertise, thinking, and hard work. Well, I want to believe that science is actually, or I want to argue that science is actually a lot more like technology than we sometimes realize. That our scientific knowledge is based on the accumulated experience and expertise, not of one genius, many people together. It works like our cars because of accumulated experience and expertise. We should believe in science as a process because by and large, it has worked. But that leaves me with one more thought. If we go back to Pascal's wager, we can ask the question, well, if we believe in climate science, and it turns out to be false, what happens? I would argue that we should believe in climate science, as well as the science of COVID-19, because if we don't and we are wrong, the consequences, as in Pascal's wager, are pretty darn dire. On the other hand, if we accept the science and it turns out to be wrong, and it turned out to just be a big hoax, well, then we will have created a better world for nothing. Thank you very much.
Grazie dunque a Noemi.
Thank you very much for this brilliant presentation. Thank you very much for explaining so well the content of your book, Why Trust Science. I have a question. Can you expand on something you said? You laid the emphasis on science as a collective venture. In the history of science, well, until recent years, we simply concentrated on the great successes of some scientists, such as Galileo. They had to fight against the system of their times, which were considered rooted and consolidated. That's a key element on which we have to think. Another point you raised in your book has to do with what's happening in the debate on climate change and the people who complain with politics. They think that they are very slow to act. I'm thinking of young people movements, Fridays for Future, and many others. They talk about diversity and the fact that embracing diversity is important. You say in your book that it is also very important to give value to diversity. Diversity strengthens our knowledge. What does that mean? In a very complex scenario like the one we are in, climate change and the pandemic?
Thank you. Those are excellent questions. And of course, the Galileo question comes up a lot, and I expect it to come up in Italy. So one really important thing that we need to remember is that Galileo was not oppressed and arrested by his fellow scientists. He was oppressed and ultimately arrested by the Catholic Church, who was the governing power of that time. So the fault there did not lay in the scientific process. In fact, we know that many of Galileo's scientific colleagues were engaged with him, corresponding with him, discussing these issues just as we would want them to be. But the Catholic Church was in many ways threatened by his challenge to Aristotelian philosophy. And so it oppressed him. And that is exactly the same as we're seeing today with climate change. Scientists are not being attacked and harassed by fellow scientists. They're being harassed and attacked by the U.S. government, by members of the U.S. Congress who have threatened to subpoena them, who have their papers, who have harassed them, and they've been threatened by the fossil industry, which is a very powerful industry. So the threat to science, in my opinion, we see historically does not typically come from fellow scientists. Argument among scientists is what we expect, it's what we need, but suppression and repression typically comes from powerful forces within society who are threatened by scientific findings. And this, of course, is one of the reasons why I argue that science communities need to be diverse. Because if science is going to work as we want it to, then scientists themselves do have to be willing to take criticism, to be able to answer tough questions, and to really listen to each other. And what I argue, and other philosophers of science argued, particularly the feminist philosophers of science like Helen Longino at Stanford and others, is that this process is most likely to work well when the community is diverse. Because in a diversity, different perspectives are brought to bear, and so we're less likely to have major blind spots. We're more likely to ensure that if there is a problem, we could say, well, hold on, wait a minute. This feels to me like you're missing a point. And we do have good evidence that when scientific communities are not diverse, they often are biased by class, race, gender, or other preferences. But when they're more diverse, those kinds of biases are more likely to be exposed and corrected.
Grazie, Naomi ORESKES.
Marco, I'm just going to stop again for 1 second because I'm having a problem with my electricity. My computer's plugged in, but it doesn't seem to be working. I'm just going to check the power cord, disappear from the screen for just while I go underneath my desk.
Allora, aspettiamo che Naomi ORESKES controlli il funzionamento del...
So we wait for you, Professor ORESKES. So there is a technical issue there. Naomi ORESKES was discussing one of the fundamental topics in this book, Why Trust Science, which clearly is a very important and crucial moment.
I'm back, but it's...
Ci sente, Naomi ORESKES?
We can, but if you lose me, then I'm just going to have to apologize terribly.
Noi la sentiamo, noi continuiamo a sentirla, Naomi ORESKES.
We can hear you, actually, so I hope that you can hear us as well. Can you hear us? Can you hear us? Yeah.
Can you hear me now?
Sì, noi la sentiamo perfettamente.
We hear you perfectly well. So, I would like to go back to the topic of climate change, because it is de facto the topic at the center of this Festival of Economics, which is devoted to growth and the environment. In your book, Merchants of Doubt, translated into Italian last year, but published 10 years ago in English, you presented a very topical aspect, and you also addressed the relationship between neoliberal policies, neoliberal economic policies, and the deniers' work and activity. So is there a connection between the two? Does it still apply today, what you wrote 10 years ago?
Yes, sadly it does. We would like our book to be obsolete, but sadly it's not. So what we showed in the book, we asked the question, why would intelligent, educated people reject the scientific evidence of climate change? And what we found was that the leaders of the climate change...
Purtroppo abbiamo un problema con...
We have an issue with the connection because Naomi ORESKES has disappeared. So let's try and see whether we can solve it. In the meantime, I will try and continue this line of reasoning. We were talking about the connection between science and the economic sector and the scientific denial. That is to say, the fact of raising doubts in people about aspects which pertain to the human-related causes of climate change. In Naomi Oreskes' book, Merchants of Doubt, there is a very in-depth analysis of this topic. This is a very interesting topic. And indeed, this is something that warns us against the temptation of being seduced by opinions which deny the extent of the anthropogenic cause of climate change. This happens when editorials are posted on websites and in newspapers and so on and so forth. Journalists here have a major role to play. There, the problem indeed is crucial at a time when fake news and ungrounded information indeed can create many problems in terms of decisions, political decisions. So I ask the technical staff whether we can reconnect with Naomi Oreskes. Otherwise, I would say that we can wait for Professor Oreskes to come back. Is there a problem with Skype? What is it? We have to see whether we can connect again with Professor Oreskes. And in the meantime, what can I say? I really would like you all to read the books published by Naomi Oreskes, including Merchants of Doubt, that was published in 2010 in the United States by Professor Oreskes. It was it has become a very famous book because she has shed light on a number of issues related to the reasons why a number of scientists deny scientific evidence which has consolidated about the anthropogenic cause of climate change. The analysis made by Professor Oreskes do not only pertain to climate change, but also safety of vaccines, evolutionary theories, which again is a much debated topic in the United States because we know that there are groups, fundamentalist and religious fundamentalist groups that deny the solidity of the theory of evolution. So Professor Oreskes made a very in-depth analysis of all these cases in that book. And she continued to do so even more systematically in the book published last year in the United States, Why Trust Science? That was the subject matter of her contribution today. She presented a number of aspects earlier on. I do not know whether we can actually, again, establish a connection with Professor Oreskes. Please tell me something about that. Otherwise, I would say that we can conclude the meeting here. I kindly ask the organizers and the technical staff to inform me about this, because it seems that it is technically impossible to retrieve the connection with Professor Oreskes. She's a geologist, a professor. She is a professor at Harvard, based in Boston, and she started her career as a geologist in the mining sector, and then she worked more in the field of science. So unfortunately, it is not possible to retrieve the connection with Naomi Oreskes, so I would say that we can conclude here. We apologize for this technical problem. We're very sorry. Thank you very much for attending this meeting. Thank you also to people following what we're doing online. And I would like to thank Claudia Marsili and Anna Lubin for interpreting Naomi Oreskes. I hope that you enjoy the festival and the rest of the festival and the next appointments. Thank you very much.